Now what we're doing in this experiment, we're going to build a wire model of the Nun's Walk crop picture of August 4, 2019. Show current going in and out like this everywhere in a disc. And when we have that Nun's Walk crop picture, if we put some magnets over it, the current goes in and out like this. So that's easy to build, and here is the thing we built, where you see the current going in and out with this wire wrap. Now the interesting thing about the Nun's Walk crop picture, it was drawn next to these cubes. There's a huge cube there, and the thing aligns with these little cubes around the outside. And this suggested to us that we might put cube magnets nearby as a way of alleviating back EMF. This is called the Halbach array. And you have normally magnets NS look like this. The Halbach array, they look like that. Now what we're going to do, we're going to use this, there's a strong side and a weak side. We're going to use the weak side of the Halbach array to reduce magnetic repulsions due to current and make the thing spin better. Now first what we're going to do is we're just going to start with an alternating polarity in the first video, and then we're going to start adding some magnets like this sideways, and we're going to put them in various locations to either reduce or increase back EMF depending on where we put them. This is the rotor we're going to start with. We're going to have an N magnet and an S magnet, an N magnet and an S magnet, sitting as little cubes on a rotor, like that. And then we're going to put more magnets around the outside in these positions. And here's our schematic drawing for the day of how to do it. You don't have to worry about it, but that's what we're going to put them over here, and we're going to see what happens. So here we go, we're going to put this rotor over on top of this thing, where it spins quite nicely. Bring it around, and we're going to measure how much current and voltage comes just first from the two magnets alone, while they're not having anything else. So this is just the 4 NS magnets with nothing. So just by themselves, these little magnets generate about 6 volts AC, just from these magnets spinning with no other magnets on the array. And then we're going to switch to milliamps, so current starts flowing through. It starts at about 23 milliamps. But what happens is slowly the rotor slows down because we're getting back EMF, repulsive currents in the wire, which slow the rotor down. Now it's down to 10, down to 3, so the thing's slowing down. Now in the next video we're going to show by adding 4 magnets in between them in the Halbach positions, all arranged S and N, we can eliminate almost all of that back EMF, and it spins almost like a perpetual motion motor. Now what we're doing here, we're adding some more magnets to the rotor along with the induction magnets, and you can see we just put them on the double-sided tape for now. We've added 4 more magnets, induction magnets and 4 others, and these are 4 Halbach magnets that are all SN relative to the others, and they'll cancel the back EMF of the others by this plan we have here. We have 4 induction magnets, and where the 4 dots are, we put 4 SN magnets going clockwise. So we're going to put the thing on the rotor, and we're going to spin it. This spins for like 5 minutes. And without any current going through, we have about 4 volts AC to start with. Now I'm going to switch the thing to milliamps. We have about 12 milliamps coming through to begin with, 13 milliamps. And we're going to watch this thing spin. We'll have hardly any slowdown of the rotor in 30 seconds. I'm going to keep filming it so you don't believe me. You agree there's no back EMF in this compared to having the 2 first magnets alone, just N and S on both sides. We've had an equal number of sideways magnets. 4 induction magnets, they're vertical. 4 sideways magnets, which is sideways. And it spins for a very long time without any electrical friction. And we're still here at
we're at 40 seconds.
40 seconds, 9 milliamps. Hardly slowing down at all. This thing's spinning even with current flowing through it, short-circuited. It doesn't slow down. So it's practically for 4 equal magnets, 4 induction, 4 sideways. They're all SN, so the induction magnets slow the wheel down and these push it forward. They're all balanced. And this thing spins for a very long time. Spin, baby, spin. If you turn the current off, it spins even longer. It's still spinning. There's obviously no or very little repulsive magnetic force slowing this thing down. I don't know how long you want to watch this for. Let's stop now. It could spin for another couple of minutes. And let's do one final trial to prove it. We're going to take those 4 magnets, flip them the other way, so they increase the back EMF, and watch what happens. We have this same device with 4 induction magnets and 4 Halbach magnets. And the 4 Halbach magnets are all north-south, going clockwise rather than south-north, so they create a big EMF. So what you're going to see here, when it spins, it'll spin freely, quite freely, until we put current on. And let's just see what voltage we've got. We've got about 8 volts AC, but now when we put current on, watch how fast it slows down. Drops right down to nothing, and the rotor spins automatically because the Halbach arrangements are all north-south rather than south-north. We drop down to very low current levels, and the thing stops. That's Halbach causing back EMF. Given previous results, we're going to put 2 round induction magnets here, north-south, and around them we're going to have these cube magnets like in the Nuns Walk crop circle of August 4, 2019. We're going to put that rotor on the wire raft which was drawn in crops at Nuns Walk, August 4, 2019, and we're going to spin it. And you see as a wire leads. Now with no current added, just voltage, we get about 4 volts. And it spins, almost doesn't look like it wants to slow down. There's almost no eddy currents. Now we're going to switch over to draw some current through the multimeter, and we'll see how much it slows down. It's not slowing much. We have 1312 milliamps AC. It's still going pretty well. There's very little back EMF from this. We're just confirming it. Spin, spin. Not much slowing. 10 milliamps, 11 milliamps. It's spinning fairly freely. It's not really hard to build one of these devices. It's based on this plan here. Induction and SN Halbachs everywhere. It's still spinning, maybe a little more back EMF than the previous arrangement because the magnets are unbalanced. We've still got 6 or 7 milliamps, but it's very easy. We have 4 induction magnets roughly balanced with 4 Halbach magnets which are turned sideways, so one pulls back and the other pushes forward, and it's still spinning fairly well. So we're at a minute here. We've still got 5 milliamps. There's not much loss of current. It's more back EMF, but it's fairly easy that to see that we've reduced it like before. Now what we've done, we've also made some bigger Halbach arrays. You have 2 big 40 millimeter induction magnets on either side, and we have 3 Halbach cubes on either side, NS, and they're all SN. And one of these back EMF backward, and these are forward EMF inducers. So one goes forward, the other goes backward. We'll put it on the array now. These are more powerful. And we'll start spinning it. That's good. My friend wants to go very fast. Now it's just on voltage alone. It's spinning quite nicely. And we have about 4 or 5 volts from that just by itself. Can spin that way for a long time. Now let's start making current. Flip it over to current. It's slowing down but fairly slowly. We had about 20 milliamps. Now we're down to 17. Let's just watch it and see if it slows down a bit. It's going quite nicely compared to just the 2 magnets alone, which we'll show you in a minute. It's spinning quite nicely. We're still at 15 milliamps. Still spinning well. Now 1312 milliamps. Still not slowing down very much. There's not much electrical friction here. Still getting about 9 milliamps. Still spinning quite nicely with 2 huge induction magnets 40 millimeters wide and 3 Halbach cubes, which are the magnetic fields of the Halbach and the other are balanced magnetically, the same strengths roughly. It's still spinning quite nicely. Now this thing is making current. We have the same 40 millimeter times 20 millimeter induction magnets. We have one little Halbach cube around the outside for each one. We're going to put it on the zigzag rotor. And we're going to see how much current and voltage is made. Spinning like before. Here we get about 14 volts, which is a lot more than before. We may have had too much Halbach influence on it. 14 volts, is spinning quite nicely. Now let's put on make some current. It's slowing down almost immediately. So you get tremendous back EMF. It's slowing down almost immediately. So that's what back EMF does if you don't have enough Halbach magnets in there. First we have 6 rotor magnets, all end poles facing down toward the wires, spaced evenly at 60-degree intervals. And they generate about 7 or 8 volts of current. And if we put AC power, they generate about 30 milliamps, but it stops quite quickly due to back EMF within about 20 seconds. You know what's really interesting, if we put 6 magnets SN sideways on this rotor with no vertical magnets, we get about 8 or 9 volts. It spins quite nicely. And then we turn to current, we get some back EMF, and it comes down from about 20 milliamps and slows fairly quickly. So we get 6 of these SN magnets, we get current and voltage and back EMF, quite surprisingly, since the field is perpendicular to the wires. Now here we have 12 rotor magnets alternating N and S, and they're all vertically down, NS, NS, NS. 12 of them go around, and they generate a nice 15 volts AC. And when we see if they stop due to back EMF, they do very quickly, and the current goes almost down to 0. So we try to spin them with back EMF. It's a very high back EMF for this arrangement. Now here we have 12 cube magnets, all with the poles horizontal, alternating between NS and SN around the rotor. 12 of them spinning, and they give about 17 volts. And when we switched to current, they start off at about 38, 39 volts, and the rotor stops almost immediately. There's so much back EMF for this arrangement, I can hardly get it to spin. So whenever we have all the magnets all horizontal or all vertical, we get a lot of back EMF current, but a lot of back EMF. It doesn't matter how we do it. Still seems to be the best arrangement of magnets on a rotor. We have 4 induction magnets 30 degrees apart on a 12-volt symmetric rotor, and on the outside we have 4 sideways magnets, all oriented the same way, SN, and they're 45 degrees away from the induction magnets. So we have a 35-degree angle and a 45, and that seems to give the best thing, and it gives equal cancellation of back EMF everywhere. However, for this arrangement, we get a bit lower voltage than normal. We'll look at it again now. So what we need to reduce back EMF are equal numbers of vertically and horizontally placed magnets. Here we have 4 and 4, making about 2.5 volts with a slow spin. And when we start to drag current from them, 9 milliamps, it's low voltage, but it'll spin for quite a long time. Now these are in ideally phased positions. So this does not slow down the rotor, where we have equal number of magnets, equal number of vertical poles, equal number of horizontal poles, all phased correctly. Very importantly, to get the cancellation of back EMF as we observed, we have 2 NS induction magnets here and here. We have some other cube magnets here, and you can see angles of 30 degrees, 45, 60, 45, 30, 45, 60, 45. These magnets here have to be horizontal with the S leading. We're going to show you what happens now if the S poles of those magnets are up, vertical, like this nearby magnet, rather than horizontal the way they were before. Now the system doesn't work. Now if we place those 4 outside cube magnets vertical with the S pole down rather than horizontal, we still get quite a reasonable voltage of about 7 volts. But if we put some current on, start from 30 amps, and it drains right down immediately, the back EMF is just very high. So having those extra magnets all vertical instead of horizontal does not work. Just for fun, we're going to flip them to north and just prove they have to be horizontal. Just for fun, we've put the 4 sideways magnets away from the others, 45 degrees away, but we put them end poles down. It spins nicely at about 8 volts. And then we flip to make current. We start off at 30 milliamps, and the rotor stops very quickly. Having those magnets vertical, a whole set of 8 verticals with poles arranged, something does nothing whatsoever. Just to conclude, we'll put them horizontal again to confirm we're doing the right thing. Now we put the magnets on the outside horizontal again as SN. We have about 3 volts to start out with. And however, when we flip to current, the rotor doesn't slow down. This is the weak side of a Halbach array. We've taken the weak side of a Halbach array and we've just dispersed the magnets around the rotor. And it sits there, keeps making about 10 amps no matter what we do. So the key feature here is not the phasing of the AC currents, but the fact that we've taken the weak side of a Halbach array and we've spread those magnets around the rotor, all the magnetism is canceling out in various places. And that's the key physical feature of this discovery. Spinning for a long time. We're still at 9 amps. This thing doesn't want to slow down. 4 vertical magnets, 4 horizontal, equivalent to the weak side of a Halbach array is what we're doing. The magnetism's canceling, but we're still making electricity. The magnetism is canceling overall, but in some places it makes electricity. So we have to have 4 vertical magnets and 4 horizontal ones. We can't have just vertical ones or all horizontal. You can't have all vertical or all horizontal. It has to be a mixture of the two. We've determined that experimentally today, and it's still spinning. I could do this. Let's do a final turn, just reverse them the wrong way and show how it stops. Now we have 4 vertical magnets and 4 horizontal ones, but I've set the horizontal so they represent the strong side of a Halbach array. We have about 12 volts, but when we flip to current, the thing stops almost immediately. The strong side of a Halbach array has a lot of back EMF. Finally, I just want to show you how well balanced this rotor is. We can put another set of magnets right over it, alternating 50-30. There's no cogging, whatever. Perfectly uniform feel. The rotor below with 4 vertical and 4 horizontal magnets spins perfectly. Perfect magnetic balance, and that seems to be the key to getting a reduction of back EMF from the weak side of a Halbach array. There's absolutely no cogging, no magnetic imbalance anywhere. You would expect this wheel just to clog up with different size magnets over it. Instead, it just spins perfectly. No sign of slowing down. Even different magnetic forces will not disturb its magnetic balance. And that seems to be the key. 4 vertical magnets, 4 horizontal magnets, arranged in the locations as shown. Thank you and good wishes. Free energy to all.